Okay. Fourth day of our Julia journey. Today we have quite interesting stuff to cover. I would like to start with one of the things that were discussed yesterday. I think it was the last topic. It was Aritra's question. And I spent some time thinking about it, and I would like to share with everybody the answer. And I already shared with Aritra. So if you don't remember, Aritra asked me about the different integer types in Julia. We have integer 16, 32, 64, 128. And these values are with regards to the memory allocation of these numbers. We have this for floats as well. And everybody knows here that in computers, these numbers are transformed from decimal scale to binary scale. And these binaries occupy a space in the memory. And for each of these integer types, we have an interval that is valid, because for integer 16, like, how far can we go with an integer number that occupies only 16 bits in the memory? To calculate this, we use this simple formula, 2 powered by n minus 1 up to 2 powered by n minus 1 minus 1. And n is the number of bits. The number of bits is 16, 32, 64, 128. So here you can see, when do I use each one of these types? When you have a number that is lower than minus 32,768 and higher to this, you use integer 32. Same for this, lower to this and higher to this, you use integer 64. And if your number is really big, if you are working with really high dimensions and large scale, and then you need to use integer 128. And this is interesting in terms of applications, because Julia nowadays is being applied to aerospatial research in NASA. A lot of good and interesting things that use this concept of integer numbers. So Aritra asked me, what's the interval for each one of these types? And I put that, and I found that to give this information to you. When you try to use an integer type to a number that is out of the range, you will have the inexact error. And to transform each number into a different integer type, you use directly this function, integer 16, integer 32, integer 64, and so on. And if you can even operate over integers of different types, but your result will always be the one with higher dimension, because of this hierarchy structure of these data types. And then if you try to transform integer type that is integer number that is out of the range of the specific integer type, you'll get this inexact error. And this is interesting because the back-end function to do this transformation is called trunc, from truncate. And then another way of doing it, you can use truncate, integer type, integer number, and then you have the transformation. So I just wanted to share this because this was a question yesterday and I was curious about it. And I wanted to share questions about this before we go to another activities. This is also opened as an issue on our GitHub. So if you go to the GitHub page, you go to issues, you can see this issue bits allocation. This information is there because I wanted to answer Aritra's question. And then I will close the issue, but everybody still has access. So if you didn't understand, and if you have question about this, you can leave your comment and we can reopen the issue about this topic. And this is important for people that work with large scale simulations. This will be a critical point of their implementation and work, day-to-day work. Okay. So let's do the exercise from yesterday to remind a little bit about the topics we covered in yesterday's class. For the chemical reactions and the catalyst package. I have asked everybody to write a function or script that could take a reaction network from the catalyst package and form a matrix with the stoichiometric coefficients. So, and we will apply the concepts of matrices that we had worked yesterday. Let's do it then. I know that Aritra wanted to practice this, so if someone wants to share their answer before I start explaining, I can allow screen sharing and then we can have. No worries. Okay, so let's go. Okay, so let's go to what I have here. We need to call the catalyst package. I hope everybody now knows how to install these packages and call these packages using the using command. So you using catalyst, and then you define the reaction network, as I showed yesterday. You define the reaction network with the rate constant, and then reactants, arrow, products. Okay, and then you will get the LaTeX notation of this reaction. Great. If you print this structure, you will see that reaction network is a type called reaction system. And then inside of this, you will have the network properties. And you will have the chemical reaction. You have all the symbolic notation of the reactants and products. That's quite cool. So if you want to contribute to this package and implement new stuff, this is important. If you just want to use it, that's fine. You can skip this part. But the interesting thing is, remember when I explained everybody about the multiple dispatch approach? We see this being used in the current implementation and the packages we are employing the use here. So all that concepts from the very first class are still important, and they are being applied in many different implementations important to chemistry. So all the structure of the language, the syntax is still good to remember and recognize their use in the applications. After you defined the reaction, you can call Rn species dot species. And when you do that, you get this is not a vector because if you see the type, it's a basic symbolic, but it will work as similarly as a vector. When you do this, we'll get this pseudo vector with the species of the reaction network you defined. So I didn't run, so let's run this. Great, great. Reaction species. Now let's see the size of this vector. The size of this vector is 5, which makes sense because we have 3 reactants and 2 products. Great. And we see here the size. Oh, I see a question in the chat. Oh, I see. Okay. Okay, so the size is 5. We have 5 elements. And we get the reaction network, and we can define reactions. Reactions is a function inside the catalyst package. And we had this one element vector with the reaction and the rate constant inside the reaction network, the one we defined. Why this is important? Because now we will access another instances of this reactions method. So I've defined this, and I want the first reaction. In this case, we only have one reaction. That's why I'm calling 1. But if in my reaction network, I had 2 different reactions, let's define in a new cell just to don't mess up with this. So reaction network 2. C2 A plus E plus F G 2G. Yeah, okay. We see here a reaction network with 2 reactions. Then I will call the reactions method and put reaction 2 inside. See, I have two elements vector because I have 2 reactions inside my reaction network. If you have a chain reaction, if you have if you're doing transition state studies, you will probably use a different states in your reaction network. And then you can access this vector. 1 is the first reaction. 2 is the second reaction. Okay. Here with the first reaction network, we just have 1 reaction, and I will call 1. Okay. And here, just a reminder, if you have more than 1 reaction, you can iterate over. Let's do with another example. For reaction in reactions, reaction network 2, print the specific reaction. We have this. We have the two reactions from the composed reaction network. Okay, going back to our plain one reaction network. After I've defined this, I can call the substrates instance. And then I have a vector with my substrates. If I do the same with the products, I have a vector with the products. This in symbolic units. So just the name of the product or the substrate, just its symbol. Now I can get I can open a reactant matrix with the dimensions of the number of reaction substrates I have. Because remember, the task is to have this stoichiometric matrix at the end. Okay? Okay. So we form this reactant matrix first with zeros, integer zeros. I have just reactants and products. So the number of rows will be 2, one for reactants and another one for products. And the number of columns will be the number of substrates. In this case, 3. But I will put length of substrates because it could be whatever size that this would still work. Let's just show the function length will give you the size of the vector. Substrates 3. These are the number of substrates we have in our reaction network. And now I form another zero matrix, but with the dimensions of the products. We have 2 products. So we will have a squared matrix because we'll still have 2. We still have 1 row for the reactants, 1 for the products. This one is for reactants, this one is for products. This one reactants, this one for products. And we have the number of columns as the length of the products vector. So we have a squared matrix because we have 2 products. And now Catalyst takes the reaction network and already parses this symbolic notation and gives us the stoichiometric coefficients when we call the method substoich. And then for the substrate, you have the substoich instance, and then you have a vector with the stoichiometric coefficients for the reactants in our network, A, B, and 2C. So it's 1A, 1B, and 2C. You have this vector. When you call prod stoich, you have this 2-element vector with the stoichiometric coefficients of the products. Don't worry about this because you will have access to the notebook, and then you can see the notation for the use of the catalyst package, because this is already implemented, the substoich and the prod stoich. This is already implemented, so you can just call it and use. And you can use this notebook as a first reference for you if you want to use that in your research. And as long as you use more, you won't need to look at the notebook or the documentation because you already have the sense of how to use it. We have this prod stoich, And now it's the interesting thing to see if people remember the matrices operations we practiced yesterday. Now we will iterate over the substrates to substitute in the reactant matrix with zeros. We will substitute the zeros in the first row, the reactants row, with the reactants coefficients. I iterate over the substrates and I take the index of the substrates. What does it mean? Let me show you. For I in each index reaction substrates print ln e and end. When you use this each index, it won't give you the value in the list. It will give you the index. So 1, 2, and 3, because this is the element 1, this is the element 2, and this is the element 3. So we use this each index to iterate over the indexes of a vector. Okay, so we use the index because we want to make sure we will put the actual stoichiometric coefficients in the right place in the zero matrix of the reactant. So we have 0, 0, 0 in the first row, the row of the reactants. But it should be 1, 1, and 2, right? So we need to replace the element 1, 1, the element 1, 2, and the element 1, 3. That's why I'm using the each index. And in the reactant matrix, I will substitute 1 with 1, 1 with 2, and 1 with 3. Why am I defining this as 1? Because this is always in the first row, so this is constant. But this I will vary according to the index. And this element of matrix is equal to the element, to the respective element in the substrate stoichiometric vector. So this for loop is saying that for each element in the matrix, in the first row of the matrix, you will substitute by one of these values. I know this is a bit tricky and you need to practice. But when you run this, let's run. Okay, great. And you run and you see your reactant matrix again, you get this. You get the values substituted. That's great. After this, we do the same for the product matrix. It's the same for loop, but now for the reaction products and the product matrix. And instead of the first row, now we'll substitute in the second row. And in the product matrix, not the reactant matrix. So I'm working with two separate matrices, the reactant and the product. Reaction, prod, stoichiometric. Same principle, same idea. We iterate over the indexes and replace the values. And then I have my product matrix. Great. And now one of the things that I showed yesterday, and now you'll see a use for it. When you want to concatenate two matrices horizontally to have this final answer. Our reactant matrix is exactly the same as this first part. Our product matrix is exactly the same as our second part. So we just use the horizontal concatenation to have our result. That's super cool because we are using a function that we learned yesterday on this. So, questions so far? This is uploaded in the Ripple story, so you can check the solution and run by it yourself. So, where's the chat? Okay. Questions so far? Before we move on to another things? Okay, great. If you need more time to practice, process the information, and then ask questions, feel free to ask in the GitHub or interrupt. And if you got it, that's great. I hope everybody could get the sense of this answer. If I didn't explain a part to something very well, you can tell me, hey, could you explain this better? Then I can try my best to do that. Okay. Now, let's move on to a very cool thing. Let's use a package for atomic and molecular simulations called MOLI. This package you install the same way you always install the packages, using pkg, pkg add, and then you use MOLI. Yes, great. And now we will first simulate a fluid acting under a Lennard-Jones potential. We will just define a certain number of atoms first, and then we will start with 100. Okay, I didn't ask. Do you want me to give 3 minutes for you to run this cell and install, or we can move on? You can put in the chat. If you want me to wait 3 minutes for you to run this cell and install the MOLI package, I can wait. Okay, so we defined 100 number of atoms. We defined a certain and a generic atomic mass. And in this package called MOLI, you have this type atom in which you need to define the mass that you put earlier. This is the unit, okay? And then you define boundaries. Okay. You define the boundaries of these atoms. And then you form a vector with 100 atoms elements inside to form our box. And you have the energy of the particle. Oops. Let's run this cell. Okay. So in this one, you are just forming. Oh, okay. So in this cell, you are just forming a big vector with 100 elements and an atom in which one in this element. That's all. And then you define the energy of the particle, the mass of the particle, the diameter of the particle, everything. Okay, great. So Now, for the simulation, you need to define periodic conditions. You need to define the dimensions of the space these particles will be placed in. And then we define this boundary. In the MOLI package, you can use triclinic boundary, rectangular boundary. We'll use the cubic boundary today. And then you define the size, the limits. 2 nanometers in the X, in the Y, and in the Z. And now, after this, you define the pairwise interactions between these particles. And we will use a Lennard-Jones potential. I won't dig deeper on this Lennard-Jones, but basically is the potential that will define how these two particles, when they come close, what's the profile of interaction between these two particles, these two atoms. Because if they come too close, what will happen? They will have a larger repulsion, they will form a bond. What will happen? So that's why you have these Lennard-Jones. And if they are so far apart, you will have no interaction between the atoms. So there are other options. I don't remember exactly now. And other options for pairwise interactions in MOLI. I can check that out if someone is more curious about it. But Lennard-Jones is a good one to test. And then we will call the placement of atoms in the cubic boundary in the cube we defined earlier. So we will just throw the atoms inside of it. Displace atoms, it's random, so we'll put the atoms randomly, and we'll set up a minimum distance between them. And then we will have another vector with the coordinates in the X, Y, and Z axis for these atoms. And then for our simulation, we will need to set up a temperature, a pretty low temperature here, 100 Kelvin, because it will be easier for us to visualize. And then based on the atomic mass, this is the unit again. When you have this 2 quotation marks and international system symbol, you can just infer that that's the unit. And you have this U. This U is an indicative that this string is a unit string. That's why you have this U before the quotation marks. Okay, is that clear? Okay. 81. I didn't run this. Let me just run, update the cell. Pairwise. Okay, great. Temperature. Now we will set up the velocities of each atom based on their mass, the temperature we set up, and then we will have the vectorial velocities, like the vector decomposed in the X, Y, and Z axis. Great, we have a new vector. So we have a bunch of vectors. We have a vector for the atoms. We have a vector with the pairwise interactions. We have a vector with the coordinates. We have a vector with the velocities. And we have the boundary conditions, our cube. Now, in the MOLI package, you have this structure called system. Again, we see the multiple dispatch being used here again with these structures when you open this parentheses and put everything there. So now we have our atoms, pairwise interactions, coordinates, velocities, boundary conditions. And now we have the loggers, and we define the system. Great. Now we define a simulator and how the temperature will be controlled over the simulation. We will use this Anderson thermostat. And this is the timestamp for this thermostat. And now we will just run simulate. Simulate exclamation. We put the system and the simulator and the number of time frames. Great. Now that we have this, let me just run the cells, run system, run simulator, run simulate, and it's quite fast. Where is that? Yes, so the simulate is quite fast. And now we'll visualize a small video, a short video for this. We'll use GL Makey to visualize. We just call the function visualize. We put the system loggers, the coordinates, boundaries, and then we define the path where we will save. I will show you. I ran this already, and I will show the saved simulation. Are you prepared? That's the coolest part. So we see the atoms. It's quite cute. I think that's quite cute. It's very nice to run this. So questions so far? Again, this will be available. So if you want to use with more complex simulations, trying something you are working on, you can use the same steps that I showed here to do the simulations. What will change is just the parameters. So you can use the same steps and define your own parameters for your research, for your applications. And now that's quite cool. Let us try at higher temperatures. Now let's go crazy. Oh, I will show, okay, before we try this 3000 one, I will show one that I ran for 150 Kelvin. So this simulation here, I ran for 150 Kelvin. And you'll see how faster the atoms move compared to the previous one. And that's expected, right? Because we'll have higher temperatures, we have these atoms occupying higher energies states, and they move faster. But it's quite cool to visualize this. And this is great for teaching too, because if you're teaching physical chemistry or physics, people that see this can understand the concept a lot better. At least I think. I don't know if there are people for education here, but I always like to mention that because it's great. Let's simulate for higher temperatures, and it's quite fast. You saw that it didn't take even 1 second to do, like, to run this. It was quite fast. So you can do in a class, you can do like we are doing here. And in your research, when you scale up to heavier atoms and larger systems, you take a bit more time, but you still can do it, and it's quite practical for your own workflows. Okay, so now to change the temperature, we just change the variable temp, use the same unit, but we need to generate new velocities because we changed the temperature. So we need to recalculate the velocities. And then we put the new velocities in the simulator. And we can change this timestamp. We can change the timestamp for a half picosecond and use the same Anderson thermostat. And we simulate again. Simulate. And we visualize again. Okay, great. This one took 2 seconds to prepare the GIF. Now let's see our beautiful simulation. See, atoms go crazy at higher temperatures. We see they're going crazy. They start, and then as the temperature increases, they move fast, really fast, which is quite cool. Another thing that we can try to do now, let's see, we could try to have larger diameter molecules or larger diameter atoms or heavier atoms. And let's see what happens. Let's double the mass of the atom and let's run the simulation again. Let's see. So we go to the steps again. I scrolled up to our first simulation, and now we will just run the cells, but now with the mass changed. We doubled the mass, and let's increase the diameter a little bit. I think that's too much. 0.4 nanometers and 60 units of mass. Great. Same cubic boundary. Now pairwise. We generate the coordinates 100 Kelvin and random velocities depends on mass, so we need to generate new velocities. System, simulator, simulate. You'll always run simulator and simulate in this sequence. And then visualize. But now, when I save, I will put 60 units just to make sure it saves with the right name. Okay. Oh, another thing. Okay. Another thing. All these simulations are being saved in the simulations folder. So if you want to visualize in your own computer, they are available. So let's compare. Let's see if we notice some changes comparing these two. So we have the 30 units and we have the 60 units. They're moving a bit slower, right? We should change with more like intensity these conditions, and then we can visualize the effect. But it's quite interesting. So we can play around with these conditions and we can see different situations, which is quite cool. Now things will go crazy, because now we will do a simulation on a diatomic system. So before we go into that, question so far? Let me stop sharing for a second. Question so far, is it too much? Are you guys being able to follow? Or is it too easy? It can be too easy and I'm explaining things wrong. So if you have comments, if someone works with this and want to give suggestion or something like that, that's very much welcome. Okay. Let's go back to notebook. In the simulation of the diatomic system, remember, we are doing these simulations for 100 atoms. But now, a diatomic system, we need to form a bond, and these atoms will be directly binded to each other. So here I'm defining the atoms again with the same atom mass. We defined earlier the nanometers, energy, and we formed this list again. And then now these things, we are using the cubic boundary. And now when you want to have the bonds, when you are defining the place atoms, when you are placing the atoms in the cubic boundary, you need to divide the number of atoms by 2 because they will be in pairs, right? So if you have 100 atoms, you need to place 50 because you will be doing you'll be binding the other 50 atoms accordingly. So you just place half. That's why you divide the number of atoms by 2 when you have this diatomic system, because you will bind the atoms accordingly. And then you have this coordinates. And now for the coordinates, we will define bonds. The bonds will be in the same axis, but they will be a bit far and 0.1 nanometers far. The other 50 atoms, they will be 0.1 far to form the bonds. And now we will define the velocities same way with the atom mass and the temperature, and we iterate over the number of atoms. Densities, no, not for this type of simulations, but I will show using the FTK how you can get the energies. But for the energies, you use another package that I will show after. Okay, great. So you have these velocities. But I think this I need to check in the documentation of the package, in the Molly package. I think you are able, depending on the application, you are able to plot an energy profile within the time, but I need to double check. I will double check if you can plot the energy profile along the simulation, and I'll get back to you. So you have these velocities. And now, to define the bonds, you will need to use this another structure, interaction list, 2 atoms. And then you use this collection of atoms. You will use 50 and then another 50. And then the bond is established using the harmonic oscillator model. Everybody loves it. And then you form the bonds, because these bonds need to be placed, and we will visualize. And now let me see if I ran this. Okay, I ran. Now I need to run this cell. Okay, we ran this, and you see it doesn't take time to run and set up everything. And I think that's a very good way of doing this simulation, because you have a lot of control over the parameters and the steps, differently if you're doing with what's the Amber, with molecular dynamics softwares. I know those are very well maintained, but sometimes you don't have a lot of control over the code and how things are running in the backend. And if you do that with Molly and Julia, you'll have a lot of control. Oh, I was trying to remember the name of the molecular simulations package, the molecular dynamics package, GROMACS. Yeah, I was trying to remember this. Let me see. Yeah, these are the implementations. But the thing that I was looking for, yes, these, I wanted to see this. Yes, that's cool. I didn't put an example of this. I should have put an example plotting these energies, but okay. Actually, I will put a homework for this, and then we practice as a homework. Because I wanted to show the visual part first, and then we can dig deeper on it. So, going back to this, we define the bonds, and then we form the list of the bonds using the specific interaction lists, and then the type of interaction we will define is bonds. But the diatomic molecules, they also interact to each other. So now we need to find the interactions that do not correspond to the binded atoms. Intermolecular interactions, basically. So here we define the eligible interactions and atoms for the non-bonded, for the intermolecular. And then we make a list. This starts a vector of truths. And then for the atoms that are binded to each other, forming the diatomic molecules, we give false as an argument. And then the ones that are truths, they are eligible for intermolecular interactions. Does it make sense? So the strategy here is to form a big vector. I will show what I mean by a vector of truths. 10, 10. Yes, this is a matrix of truths. And then representing by bits, you have 1 as true and 0 as false. And then in this will iterate over this matrix of truths and will substitute the elements in the matrix that are binded to false. So we are using the concepts again. We will using the concepts of matrices operations to do these simulations, to run these simulations. They're all over the place. They're everywhere. That's why we need to practice. Okay, we run this. We have the legible interactions for intermolecular ones. And then we find the neighborhoods of these diatomic molecules by putting the eligibles, the number of steps for this optimization, and the cutoff, the distance. Great. And then for the neighborhoods and the intermolecular interactions, we define Lerner-Jones again. We define the system, simulator, same parameters, and simulate. So the order is system, simulator, and simulate. And then visualize. Let's go to the diatomic. Oh, I see. Diatomic. Here, let me just close this and open again because it's too zoomed. Oops. Where is that? Just because it was too zoomed in, I need to close. Okay, let's go to the diatomic. It's beautiful. We now see the simulation with the diatomic molecules and the bonds are being shown, which is quite cool. And then what you can do, you can change the, let me update this on GitHub, update Molly simulations. Great. I know that's a lot of information. So, questions so far? For tomorrow, oh, yes. Let's go back. This is oh, okay, I found it. Yes, in this cell. Here, we defined, remember that we placed only half of the atoms, because for this case, we are doing the diatomic. So we need to form the bonds between two atoms to form the diatomic system. And when we use the place atoms function to put the atoms inside the cubic boundary, we just used the half of the atoms. We defined 100, but we just have 50 coordinates. Okay, so this will iterate over each one of these 50 atoms, and to place the atoms that will be bound to these ones, it will keep the same y and z axis, because in the diatomic system, it will be in the same y and z axis, but it will be displaced in the x. So this will iterate over the coordinates and place a new atom next to it, and the distance that will form this bond is 0.1 nanometers. Does it make sense? That's why this is 0 because it will be in the same y and z axis. Yes, great. And this in the x-axis will be displaced. And oh, great question, actually, because yesterday I showed how to broadcast in the operations between vectors, matrices, and how you sum up two vectors, two matrices. And you have this dot notation. Remember the dot notation. I know we went through that quite fast, but yes, we have this dot notation that will sum up at each element. Each vector element will be summed up to this. So we will have the 50. Actually,
So actually, before this step, two atoms are superpositions on each other, right? On top of each other, right?
yeah, exactly.
So we are just moving towards the x direction. We are moving
Zero
one
point 0.1
atom to,
nanometer.
yeah.
Yes. And then after doing this, see here we had 50 elements in the vector. And now after running this for loop, we have 100 elements in the vector element in the coordinates variable. So yeah, this is the role of this part. Does it make sense? Let me update. One thing that I will do for future versions of this course, and I was discussing this with Aritra. You know that I'm always asking you to install the packages inside the Jupyter notebooks. But for future versions of this course, or for people that just want to clone the repository and practice with the code that is here, I will create a Julia environment with all the packages previously installed. So when you clone it, you already have all the packages you need instead of need to install in each notebook, because I think this reduces the load and makes the notebooks more clear. But yeah, this is something I'm thinking about doing for next versions, or just to leave in the GitHub and for people that want to do to make the exercises, which is great. I can show, I don't think I will show that now, but I think I can show how to create environments in Julia. That's great. But this is for people that want to work with modules and software development. Okay. So this was our fun explanation about Molly. And I will show another examples, not with code, but like the videos showing what else this Molly package can do. These simulations can be expanded to physical models like gravity. Here you have two bodies in a ellipsoid format. They have a gravitational attraction between them. You can simulate a planetary system. I didn't want to focus on the code for this too, because we try to focus more on chemistry applications, atomic applications. But this is quite cool because you can have this planetary system simulation. You can have a bunch of different physical models simulated by the Molly package. Which is quite cool. So I suggest you to take a look at this. And for tomorrow, we'll have an exercise. I will leave this for tomorrow as an exercise, so people that want to practice. We will run a simulation on a protein. And the code is already available in the practices folder. I will do some changes on some minor changes on that today, for the sake of visualization after the simulation. That's why we won't run this protein simulation today. We'll run that tomorrow. And when you install, and this I will show in the terminal, when you install the Molly package, okay. So remember when you install Julia, you have this .julia folder, right? And then you have the packages folder. And here are the packages you have installed. If you go to Molly, you will see in one of the installations, these installations are like hashed. So when you install, you have a hash of this installation. It's like identification number. You go to data and you will see some data and some examples here. Some PDB files that when you install, you already have them to do these practices. And then by doing that with this, you can extend to your own proteins of interest or to your own systems of interest. Here you have some sort of parameterized force fields. And I think if you work with parameterization of force fields, you can implement them in the package, because you can move them into this package and you can have XML. You can put the information here using this formatting. And then you'll have the right information and the parameterized force field for what you need, which is quite great because it makes it easier to work with parameterized force fields. I think it's easier. Correct me if I'm wrong, because I didn't work with Gromex, Ember, and this molecular dynamics softwares too much. But I think it's easier if you're working with parameterized force fields to work here than to go through Gromex and implement this parameterized. I think so. So correct me if I'm wrong. Questions so far? Let's move to another practice. Okay, we still have 3 minutes. I think we can do it. Day 5. Yes, great. So now we'll go to another cool thing, the DFTK package. The DFTK is the DFT toolkit in Julia. It's good for solid state because it uses plane waves. I'm a Gaussian orbitals person, so no plane waves for me, or like for my research. I don't use plane waves, but I know a lot of people love plane waves, which is great. But for me, it's just like Gaussian. And then if you want to use Gaussian now, time for advertisement. But if you want to use Gaussian basis, then you need to go to my package, the quantum foci, and then you will have access to all sorts of Gaussian type orbitals you want, and primitives and things we in electronic structure methods love. Okay, going back to this. I asked you to install the FTK. At this point, I think everybody remembers that. To install the same procedure as always, using pkg.add, and then name of package, okay, in this case, dftk, and then using dftk. Great. Now, we will define, to use dftk, you will define a lattice. You define this lattice constant. In this case, 10, and you define as a matrix the lattice. One thing that is important to mention, the functionals supported by dftk are LDA and some GGA. Further supports are being implemented. So I think in the next month or 2 months, because sometimes I go to the DFTK meetings and they talk about that. I don't actively participate on the development of this package, but I participate in the Julia Molecular Simulations organization, and this is one of the packages we have in the Molecular Simulation organization. And I think in 1 or 2 months they will expand this range of functionals available, which will make it even more interesting and nicer. So we define the atomic positions. In this case, let's go to our beloved hydrogen. We define the element pseudopotential. This is from the FTK, this element PSP. We define hydrogen as a symbol, and then we load the pseudopotential. And this, I will show this in the terminal. But this you have access when you go to the installed package. If we go here, Julia, packages, DFTK, CD data, PSP. PSP stands for pseudopotentials. You'll see LDA or PBE, and then you go to LDA. You'll see the ones that are supported and the atoms that have LDA available in the DFTK package. So don't feel afraid to go and play around with the files inside the packages you install. Just be careful if you want to delete or modify them to don't break the installation. But Julia is quite flexible, so if you break the installation of a package, you just uninstall and install again with no worries, because in Python is a big headache if you want to install again, because you have shells of conda environments and a bunch of things. I don't desire this for people, like this headache for people, so just use Julia and uninstall and install again if you break the installation. But don't feel afraid, play around with the files. If you want to make changes in some of these pseudopotentials, if you want to parameterize these pseudopotentials, just make sure you have the same formatting, but you can come here and put your own parameters for the pseudopotential. Just completely fine. So we go here, we define LDA for hydrogen, we load this pseudopotential. Remember, you don't need to install this pseudopotential. This is already installed and already in your computer when you add the DFTK package. And then we define atoms, we define 8,2 hydrogens. And then we define the positions in the opposite extremes. And then we have the coordinates here, the positions here. You can do this for different atoms if you want to. For example, here I'm showing you can define the hydrogen, a pseudopotential. You can load the pseudopotential for hydrogen and a pseudopotential for silicium, and then you can do like mixed atoms, silicon. You can do that, and then you define positions again, and then you create a model. Your model, you put the lattice, the boundaries, you put the atoms that you defined here, in this case here, and the positions. And then this model will create the lattice, it will calculate the unit cell volume, will show the atoms, H2, the potentials, number of electrons, spin polarization, if any, and the terms, kinetic, atomic, non-local, evol, PSP correction, Hartree, exchange and correlation. Great. And then you define a grid for your basis, for your plane wave basis, and then you put the model, you define the cutoff, you define the grid, and then you run an SCF. It's quite efficient and fast, this SCF. So in 120 milliseconds, you will run in your SCF convert, and then you can do, from this, you can get the occupancy from the SCF calculation, the occupations, the energies for each one of the terms, and the total energy, which is quite cool. Questions so far? It's quite simple to use, actually, because, again, you can have a lot of control on this. That's a good question. So, instead of explaining, let's explain and show. Let's show and tell. Our favorite function, what is type? We love type. When you have this column in Julia, you have a symbol. And when you have the quotation marks, you have a string. This symbol allocates less memory in your computer than a string. So sometimes when you are defining literally atomic symbols, you use the column because you are dealing with symbols of atoms. That's why. So it allocates less memory. They're quite fast and easy to manipulate. That's why people use that when they are dealing with atoms. Did it answer your question? So if you do type of, you'll see this is a symbol, this is a string. A lot of people work developing methods for symbolic computation. That's quite interesting. More questions? We can continue. So now let's plot DOS for a metallic system and see the Fermi level for this metallic system. So here, this is the same way you always follow the same procedures to define inputs for your calculations, for your computational simulations and calculations. You do the same in Julia when you are using these packages. It's basically the same procedure. So once you define a workflow, You just go through that and repeat that and change parameters, change atoms, change systems. So it's quite flexible. You define again the lattice. You load the pseudo potential. Remember the atomic symbol, as I think Francis just asked. You load the pseudo potential. Again, this is already installed, like this is already downloaded. You define the atoms, you define the positions. And now we will use PBE, not LDA, for a simple example for this metallic system. We define the cutoff, the temperature. In this case, because we want to analyze the Fermi level, we define a temperature and a smearing. And here I put the different methods supported for this, but we are using Fermi Dirac. We define the cutoff, the temperature, spacing between the atoms, and then we define the DFT model. We put the lattice, we put the atoms, positions, the exchange of correlation functional, temperature, and smearing. Because in this case, we want to analyze the DOS. Here, you define the model, you have the unit cell volume, you have smearing, you don't have the same polarization, but you can define it. And those are the things we want to calculate. Now we want to calculate entropy, exchange and correlation too. And then we define the grid for minimal spacing between the atoms. We define our beloved plane wave basis with the model, cutoff, grid. And this grid consider the metallic interactions. And we run the SCF, again, quite fast. We have this SCF, and then we have the energies of the SCF. Here we can see the elements, the kinetic, atomic local, atomic non-local, evolved, pseudo potential correction, and the total energy. And the occupation, we can see these occupations are important to understand the Fermi level, right? So we see that the Fermi level is the one that is the latest occupied. And then we plot the DOS. And then we have this green, we have this green line defining the energy of the Fermi level, which is quite cool. So that's why I was saying that this is quite useful for people working with solid state. And I recommend the homework for tomorrow is the one with the protein. Then you'll kind of have the code here. But I don't know if it is too much if I give a homework with the FTK too. I don't know. What do you think? Because now I think we are a smaller class. So I think we have time to discuss those things. Let me update the FTK tutorial. But yeah, I think it's quite interesting, and the way you use these applications in Julia is really cool. And we will do some further practice on the FTK tomorrow. But because in the FTK, you don't have only the SCF procedure implemented. You have direct minimization implemented with the common gradient methods, which is quite useful. And then I've compared the performance between the direct minimization. In the direct minimization, you define the tolerance. Actually, let's do that today because we still have some time. So here, for this comparison, I defined the pseudo potentials for silicium. Again, lattice, the lattice constant for silicon, the positions, the LDA model, the plane wave basis. Great. And now I run SCF here. And I run direct minimization. In here, you can compare times and accuracy. You see the direct minimization is quite slower if compared to SCF. And it takes more time to converge, like 43 cycles, while SCF takes 9 cycles. That's why we widely use SCF in our calculations. But this is something interesting to show. For people that like, oh, okay, but questions so far and the things I showed with the FTK. I get excited with those things and then I start talking. If no one interrupts me, I will keep like throwing information. Let me stop sharing for a bit. Yeah. Okay, questions so far? I want to show just one last thing with the FTK and then we are done for today. If you use ASE, the Python package for atomic simulations, you can also interface that with the FTK. So the interoperability in Python, interoperability stands from the interaction you have between different programming languages. And Julia is quite good at it. And you can have a lot of interactions between ASE, between Python and Julia, basically. And then here you have this ASE convert package, and you call PyConvert. You have abstract and abstract system. This abstract system is a type in the FTK. And you build a bulk with silicon using ASE, and you transform that, you convert that into a DFTK abstract system. So you can use your ASE into DFTK, which is great. And then you create the model with the pseudo potential, the plane wave basis, and you can have the density differences. That's what we will run here. The difference in densities within the lattice and out the lattice. And we will have this normalized and oh, okay. I think when I ran this, it didn't get the variable. Okay, running again. Don't need this because we're already using the FTK. And then we, using the FTK, we have this SCF default callback. When you calculate the densities and update the densities, we will plot this. And we have this self-consistent field calculation, the SCF calculation. Let's do the following, run again. The conversion takes some time because of the interoperability. Is not for free. You don't have this for free in terms of computation time. It took some seconds. Okay. Okay. Perfect. Now we have that. Great. Diagonalization. We have the alphas. We have the log of the density of the energy. And then we plot this log here for each step of the SCF. And then we can see the convergence, which is quite cool. So this is what I was saying about the control over the calculations, which I think is quite interesting. Let me update this on GitHub, update the SCF calculations. Yes, great. I think we covered everything. So questions so far? I hope you enjoyed today because we had a lot of applications. And we saw a bunch of the, how can we use Julia in computational chemistry, the major idea of the course. So I hope you enjoyed it and you use these notebooks to practice. Oh, I cannot hear you, Gustav. I think you're muted.
It's okay. I did some work from home
Oh,
today,
oh, okay.
so I'm here with my wife talking a little bit about the course.
Oh, I see.
It's not chemist, so
I hope you enjoyed. I will stop the recording, and thanks everybody who came here, and we're almost done with the course, but I want to say that it's been a very good time for me. I'm having a lot of fun interacting with more people that are passionate about computational chemistry and programming. So I'm very grateful for that because it's a good opportunity for me, and it's really good to be here. It's a great pleasure. So I will stop there.